Welcome to the Physics Almanac. In this video, we're going to be deriving Kepler's laws of planetary motion from Newton's laws of motion and his law of universal gravitation. In this one, we'll be setting up the equations of motion, and over a series of videos, we'll cover each law one at a time. I rated the physics level in this video as intermediate. It does have some calculus, but don't let that scare you. If you don't know any calculus, everything we do mathematically will be explained physically, so you'll be just fine. So first thing, let's go over Newton's laws. Newton's second law is actually just the definition of force, and it states that the net force on an object is equal to the time derivative of the momentum. The time derivative just means the change in momentum over the change in time over a very small time interval, essentially instantaneously. Momentum is defined as mass times velocity. These quantities with little arrows above them are vectors, which are themselves just arrows. They have a certain length and they point in some direction. The velocity is defined as the time derivative of the position, which is just the change in position over change in time over an infinitesimally small time interval. I'm going to adopt the common notation for time derivative as dot. So r dot is shorthand for dr over dt. So anytime you see dot, just remember this means time derivative. The time derivative of the velocity is defined as the acceleration. The acceleration is two time derivatives of the position, so we write that as r double dot. In the case that an object has constant mass, this time derivative of momentum reduces to mass times acceleration, and that will be applicable for this video. So now that we have our definitions down, let's set up our scenario. We're going to have two masses, which I'm going to call m1 and m2. This could be the sun and a planet, or it could be any mass you want. It will hold for any two masses. We need to pick an origin, so I'm going to pick a random point. This is where every position is going to be measured relative to. The position of m1 is an arrow that points to m1, or a vector, which I'm going to call r1. And it points to the center of m1, or I should say the center of mass of m1. Similarly, I'm going to call the position of mass 2, r2. According to Newton's law of universal gravitation, these two masses will exert a force on one another, the force of gravity, equal to the following expression. So the force is proportional to each mass and inversely proportional to the distance between them squared, and it points from one center of mass to the other. This thing r hat, this is just a vector, and actually it's just the direction part of the vector. So this just says the force points along the line connecting one center of mass to the other. And the negative means it's attractive. So now let's define a vector that points from mass 1 to mass 2. This is the position of mass 2 relative to mass 1. And if you follow these arrows, you'll see that this arrow or this vector is equivalent to going backwards along r1, so negative r1, and forwards along r2. So it's equal to r2 minus r1. So now let's plug this into Newton's law of gravity. The force that F1 will feel will equal negative g times m1 times m2 divided by the length squared of this arrow r2 minus r1. The absolute value signs here just means the length of the arrow r2 minus r1. And I'm calling this direction r hat 1, 2, the direction of r1 from r2. So that would actually be backwards along this arrow. Now it's negative. That flips it again, so this force on F1 points towards M2 in the direction of R2 minus R1. And since this is the only force, it's equal to M1 times R1 double dot, according to Newton's second law. Similarly, mass 2 feels a gravitational force from mass 1. And this force is exactly the same since it's the same masses and the same distance, only it points in a different direction. R hat 21 is the direction of mass 2 from mass 1, so the same direction as this arrow here, but it gets a negative, so the force points towards mass 1. And again, this is the only force on mass 2, so it's equal to m2 times r2 double dot. Now we need to solve these two equations of motion simultaneously. First thing we're going to look at is the center of mass motion of the system. If you're finding this video helpful so far, please be sure to like and subscribe. Maybe share it with a few friends, leave a comment, and if you'd like to support the channel, there'll be a link to my Ko-fi page at the end of the video. You can also find it in the video description. So let's redraw our schematic here. as well as our two equations we need to solve. And now I'm going to make a slight simplification in the notation. R12 and R21 are just opposite directions, which is either along this direction R2 minus R1 or the opposite direction. So I'm just going to call this vector R2 minus R1 little r. F1 is the force on mass 1 and it points in the direction of little r. So I can rewrite it in terms of little r instead, where little r hat is the direction of r, and r without an arrow or a hat is the magnitude of little r. So just the length of that arrow. The force on M2 points towards M1. So we can also rewrite it in terms of little r, and the only difference is it points in the opposite direction. The center of mass of a system, which I'm going to call capital R, is defined in the following way. It's the sum of the positions of each mass weighted by their individual masses and then divided by the total mass of the system. Moving forward, I'm going to use capital letters for everything related to the center of mass coordinates. So first thing I'm going to do is I'm going to label the total mass of the system capital M, which is going to simplify my denominator. Now, the net force on the system is just the sum of all the forces. So that's going to be F1 plus F2, which is equal to M1A1 plus M2A2. Remember that A, acceleration, is just R double dot. And if we take a look at this quantity, that is just two derivatives of the numerator of the center of mass position. So this is equal to the total mass times the acceleration of the center of mass. All I did was move capital M up here and take two time derivatives. But F1 and F2 are exact opposites of one another. So this whole thing is equal to 0. If the acceleration is 0, that means the velocity is not changing. So the center of mass velocity must be a constant. Doesn't have to be 0, but it doesn't change. This should not be a surprise to you, as there are no external forces on the system, and Newton's first law says that in absence of external forces, the momentum is constant. Momentum being mass times velocity. Now, constant so long as the observer is in an inertial frame. Newton's laws of motion only hold for inertial frames, a frame that is not accelerating. Okay, so far so good. We've just recovered Newton's first law, so that's a good sanity check. Now that we've figured out the center of mass motion, let's take a look at how these two objects move relative to one another. Taking a look at the blue equation, we see that there is an m1 on both sides, so we can divide that out and get the following expression for the acceleration of mass 1. In the case of the orange equation, it's mass 2 that divides out, giving us a similar equation for the acceleration of mass 2. Notice that the acceleration of each mass is independent of its own mass. Now, both these equations only depend on the r position, little r position, this vector here, r2 minus r1. So if we subtract the two, that's going to give us the acceleration of r2 minus r1, or little r, and that's going to be equal to negative g capital M, which is the total mass of the system, divided by r squared in the r hat direction, or I should say in the negative r hat direction. Okay, this equation doesn't look too complicated to solve. It's just two time derivatives of r, and it only depends on r. But you have to be a little bit careful because r is a vector. So let's be explicit about what r vector is equal to. It's equal to its length times its direction. So it's got a length r, and it points in the direction r hat, the direction of this arrow. Now what we want is r double dot, two time derivatives of this vector. So let's first take one time derivative. If you've taken calculus, you'll know that when you have things being multiplied, you have to use the product rule. Just to remind you, the rule is you take the derivative of the first quantity times the second, and then the derivative of the second quantity times the first. If you don't know calculus, all this is saying is the change of this quantity, r vector, is equal to the change of its length times the direction it's pointing, plus its length times the change in the direction. So in this case, the length changes, but the direction doesn't. And in this case, the direction changes, but the length doesn't. The only tricky part here is figuring out how does the direction change. So let's imagine these two objects are moving relative to one another. A split second later, this vector r might be pointing in this direction. So this dotted vector is just r at a time t plus dt, where dt is a very small time increment. And remember, we're assuming that the length has stayed the same. So the change in our vector r is going to be this green arrow, which I'm going to call dr. It's a tiny change in vector r after a tiny amount of time has gone by. And I'm going to call the change in this angle d phi. Dr now is essentially an arc length. An arc length is equal to the radius times the angle. Since dr is a vector, it also points in a direction, which I'm going to call phi hat. Phi hat is the direction perpendicular to r, or r hat. The reason we know it's perpendicular is because we've assumed that the length hasn't changed. And the convention is to call the positive phi hat direction a counterclockwise rotation. We can now divide this by dt to get dr over dt, which is what we're looking for. And remember, this is dr over dt in the case where the length has not changed. Now all we have to do is match this expression to this one. And therefore, dr hat over dt must be equal to d phi dt times phi hat, which is equal to phi dot times phi hat. So now we found r dot, but we don't want r dot, we want r double dot. So we have to take a derivative of this expression. Both of these terms have products in them, so we have to apply the product rule to both of them, giving us this long, scary looking expression. Don't worry, it's not as bad as it looks. These first two terms are the derivative of this guy right here. So first we took the derivative of r dot, which gave us r double dot, while holding r hat fixed. Then we hold r dot fixed and take the derivative of r hat, which we already figured out was phi dot phi hat. Now we have to take the derivative of this term, and there's going to be three terms since it's three things multiplying one another. We first take the derivative of r, giving us r dot. Notice that this term is equal to the previous term. Then we hold r and phi hat fixed and take the derivative of phi dot, giving us r phi double dot phi hat. And finally, we take the derivative of phi hat, holding the rest fixed. Now we have to figure out what is the derivative of phi hat. And we're going to play the exact same game as we did to find the derivative of r hat. Imagine a split second later, dr points in a slightly different direction. So this yellow vector is dr at a time t plus a small increment dt. I'm not going to actually do it here because the drawing is going to get messy, but it's essentially the same procedure as we did with the green vectors. The change in dr will be the yellow vector minus the green vector. So we go along yellow and backwards along the green vector, and that's going to give us an arrow that points in the negative r hat direction. And it changes at the rate that this angle d phi changes. So the time derivative of phi hat is negative phi dot r hat. So now we're going to have terms that point in the r hat direction and terms that point in the phi hat direction. So we can group these like terms together, giving us this following expression. Now that we've figured out what r double dot is, we can substitute that into our equation of motion. And all we have to do now is match the directions on each side of the equation. So first we group all the terms in the direction of r hat to get the following equation for the length of r. This tells us how the length of r changes with time. And if you've taken any physics, you'll recognize that this term here is just the centripetal acceleration. If you're going around in a circle at constant speed, your centripetal acceleration is equal to r phi dot squared, but the radius doesn't change since you're going around in a circle. To figure out how the radius changes, we need to look at the force in the radial direction and subtract off the centripetal acceleration. For the phi hat direction, there is no term on the right side of this equation, so the term on the left side must be equal to 0. Now we have two equations of motion that we need to solve simultaneously, and that will give us orbital motion. And we're going to do that in the next video, which is going to lead us to Kepler's first law of planetary motion. So if you'd like to see how that's done, be sure to like and subscribe, and click the bell to be notified for the release of future videos. And if you'd like to support the channel, you can go to my Ko-fi page, or you can leave a super thanks. Thanks for watching, and I'll see you in the next one.